Hello, everyone. Welcome to the Parsons Technical Webinar Series. I'll be your host today, Jessica Bennett. Today we have with us David Patch and Christy Diller presenting on degradation of PFAS using catalyzed chemical oxidation. We'll go through a few housekeeping items first on the next slide. We will be keeping all phone lines muted throughout the presentation to keep background noise down. If you have a question, you can enter into the chat feature at any time, and we will answer it at the end. You can also hold on to your questions and ask them live during the Q&A session at the end of the webinar. This webinar has been approved for 1 professional development hour or PDH credit. If you would like to receive a certificate for that PDH, there will be a link to an attendance form posted in the chat several times throughout the webinar. There will be 3 multiple choice questions you'll need to answer, so please take a look at those, and we will also post those in the chat in case you have any issues accessing the form. If there's any questions or problems accessing that form, please just send us an email at daniela.savin@parsons.com. And finally, this webinar will be recorded and will be posted on Parsons' YouTube channel in the next few days. Next slide. So just a brief agenda, we'll introduce our guest speakers, followed by a core value moment before we get into the technical presentation, and then we will wrap up at the end with questions and answers. So a little bit about our 2 speakers today. David Patch is a PhD with 5 years of experience in environmental research and development, specializing in the analysis of legacy and emerging contaminants such as PFAS. He's a senior scientist focusing on R&D here at Parsons and has his PhD in chemistry. Christy Diller has over 18 years of experience with environmental investigations and remediation, focusing on in situ groundwater remediation and emerging contaminants. She's a geologist and PFAS subject matter expert here at Parsons with a master's in geological sciences, and she's also a professional geologist in California, Oregon, and Wyoming. And with that, I will hand it off to Christy for the core value moment.
Thanks, Jess. Parsons has 5 core values which guide every decision we make and define our company culture. Today, I want to focus in on our sustainability core value. Sustainability comes into play for remediation because not all remedial technologies are environmentally friendly. While cleaning up a contaminant, some remedial technologies may have a large environmental footprint, such as excessive use of energy or lots of greenhouse gas emissions. Green remediation is the process of examining the environmental footprint of site cleanup activities and taking steps to minimize that footprint. Green remediation best management practices focus on the core elements of greener cleanups, reducing total energy use and increasing the percentage of energy from renewable resources, reducing air pollutants and greenhouse gas emissions, reducing water use and preserving water quality, conserving material resources and reducing waste, and then finally protecting land and ecosystems. Per and polyfluoroalkyl substances, or PFAS, contamination has become a widespread global issue due to its extensive use since the 1950s. PFAS exposure has now been linked to a variety of health risks, including increased cholesterol levels, liver damage, thyroid disease, reproductive issues, and increased risk of certain cancers. They're also known for their high mobility, meaning they can move easily through different media like soil, water, air. And then they're also recalcitrant due to the exceptionally strong bond between carbon and fluorine atoms in them. So that makes it very difficult to break them down under normal environmental conditions, meaning they don't readily degrade or break down into less harmful substances on their own. So Parsons' Internal Research and Development Program, or what we call our IRAD program, has been exploring a variety of methods for PFAS degradation and destruction. One large focus, and the topic of our presentation today, has been on developing an in situ PFAS remediation method that would be more sustainable by minimizing energy requirements, greenhouse gas emissions, and waste. So this presentation is going to be focused on our newly patented technology called Hot ISCO. So here's our presentation outline, just to give you a general idea of the content we'll cover today. David's going to start with some background on PFAS remediation, describe the hot ISCO technology, and then review some laboratory optimization studies that have been completed this year. Then I'll review results from a recent field demonstration of the technology before wrapping up with some key takeaways. So now I'll pass it off to David to start the technical presentation.
Excellent. Thank you very much, Christy, and thank you everyone for taking time to attend our presentation here today. So, what exactly are PFAS? Well, PFAS, or per and polyfluoroalkyl substances, are a group of thousands of fluorinated organic chemicals with widely reported detection in environmental matrices and humans. They are persistent in the environment, and as Christy discussed, they have associated toxicity values with them. We often talk about PFAS as if they're one comprehensive group of chemicals, but within that group, we have various subgroups, which we identify based on the degree of carbon chain length fluorination, as well as their functional head group. We have perfluorinated alkyl acids, such as PFOS and PFOA, which are two of the most common PFAS studied. And we also have polyfluorinated compounds, such as fluorotelomers. We have here 6,2-fluorotelmer sulfonic acid, or 6,2-FTS, shown here in the bottom right. There are many challenges that have been encountered with managing PFAS-impacted media, including analytical detection, low screening levels, often in the parts per trillion range, and the fact that many PFAS are resistant to chemical degradation. As Christy discussed, the carbon-fluorine bond is the strongest bond in organic chemistry, and it is incredibly difficult to break down through natural or chemical processes. With this in mind, we can look at the number of different remediation techniques and technologies that have been developed for the removal or destruction of PFAS in solid and aqueous matrices. This is by no means an exhaustive list, and the number of technologies for treating PFAS continues to grow by the day. But for solid matrices, we often have techniques such as thermal desorption, smoldering, incineration, or disposal in landfills. And for aqueous matrices, we often have techniques such as absorption, supercritical water oxidation, membrane filtration, or photocatalysis techniques. The use of chemical oxidation is a unique PFAS treatment technology in the sense that it can be applied for both solids as well as aqueous matrices. So, chemical oxidation is the removal of electrons from a target compound to the oxidizing agent itself. This results in compound breakdown. Chemical oxidation as a remediation technology can be applied in situ or ex situ, using common oxidants such as hydrogen peroxide or persulfate. The application of in situ chemical oxidation, however, does have challenges associated with it. Using it in situ limits the number of available activators that you can use to activate and initiate your oxidative degradation process. Furthermore, complex matrix effects and geochemistry can further complicate the application of ISCO to destroy target organic contaminants. In situ chemical oxidation has been well developed for the treatment of non-fluorinated organic molecules such as TCE or DNAPL. We have a graphic here on the right that illustrates a typical application scenario for ISCO, in which an injection well is prepared and used to inject oxidant as well as your activator into your contaminated aquifer for the targeted destruction of organic contaminants in situ. Now, when we're looking at chemical oxidation as a whole, we need to look at the activators that we use to initiate the process. Two of the most common activators for chemical oxidation are ultraviolet light and thermal activation, which are both examples of direct activation processes. Using ultraviolet light typically results in the fastest activation rate for oxidants, as well as enables the use of complex photochemistry. However, UV light is a high energy process and struggles with complex matrices. Furthermore, using ultraviolet light is really only applicable for ex situ applications. Thermal or direct activation using thermal energy is a moderate activation rate and can handle complex matrices. However, just like UV, it is a high energy process and involves complex thermodynamics that have to be studied and well understood for the site of interest. And while thermal can be used to activate oxidants in situ, it is more often applied ex situ due to the high energy demand requirements. This brings us then to metal activation processes, which is considered a catalytic activation process. Using metals to activate chemical oxidation requires little to no energy itself. You are able to take advantage of tunable metal chemistry by selecting different metals or combinations of metals. Using metals to activate chemical oxidation can be applied in situ as well as ex situ. The main drawbacks of metal activation, which can be changed to act as a benefit, is the slow activation rate and the requirement of detailed optimization. This optimization is going to be the focus of the first half of our presentation here today. So as Christy discussed, Parsons has recently completed their patent for the hot ISCO remediation technology, and the patent itself covers the metal activation and elevated temperature chemical oxidation for the degradation of PFAS in situ or ex situ. Parsons Hot ISCO was initially developed in the laboratory environment between 2020 and 2024 and underwent consecutive field pilot tests from 2023 to 2025. Currently, we're investigating a second laboratory investigation focused on optimization and mechanistic investigations, and that has started this year and is currently ongoing. The patent was granted and published in May 2025, and efforts are ongoing to continually optimize the technology and evaluate it against increasingly complex sites and media. When we're looking at hot ISCO and the chemistry underpinning the overall reactions, we have to understand the process between our oxidants themselves and our metal catalyst activators. The overall chemistry is increasingly complex as you add in more components, and even this four-step reaction we show here is highly simplified from what is actually going on under your standard site. However, we can sum a lot of these different steps into our overall net reaction we see down here, which is effectively the persulfate molecules or our oxidants reacting with water in the presence of our metal catalyst to form sulfate radicals, the sulfate anion, and the peroxomonosulfate radicals. It's these radicals that are responsible for initiating and driving the degradation of PFAS when applied in situ or ex situ. The sulfate radical, which is the main radical that we're targeting for ISCO, is a strong oxidizing radical, capable of directly destroying organic molecules, and this is the overall desired reaction of ISCO. However, sulfate radicals can react with inorganic compounds that are present in your matrix, creating weaker but differently selective radicals, and typically this is an undesired reaction. Under neutral and basic pH conditions, the sulfate radical can react with hydroxide ions to form sulfates and the hydroxyl radicals. In the presence of carbonate, your sulfate radical can react with carbonate anions to form the sulfate anion and carbonate radicals. We have a table here on the right showing the reactivity of PFAS, PFOA, and 6,2-FTS to our different radicals that could be generated as a function of the geochemistry in your site. And as we can see here, while hydroxyl radicals and carbonate radicals can initiate the partial degradation of PFOA and 6,2-FTS, we really do want to target conditions that promote and facilitate the generation of sulfate radicals. It's those sulfate radicals that are able to achieve degradation of our PFAS of study. So the overall objectives for our lab development and optimization were as follows. We know that high energy processes such as high temperatures or UV light can activate persulfate to achieve significant degradation of PFCAs and fluorotelomers. However, we can use low energy catalysts to make the process overall more efficient and more environmentally friendly by reducing our overall energy inputs. Using metal activation, such as that in hot ISCO, does require significant development and optimization to first and foremost understand the underlying chemical principles driving PFAS degradation and optimize those chemical principles to maximize PFAS degradation. And the work presented herein is a summary of our 2025 lab optimization studies. Before we jump into the data itself, we should briefly cover our materials and methods used in the study. We investigated the degradation of PFAS, PFOA, 6,2-FTS, PFBA, and TFA, or trifluoroacetic acid, which is an ultra-short chain PFCA. We used sodium persulfate as our main oxidant, and we looked at a variety of metal activators, eventually settling on silver as our main activator of investigation. We investigated several different parameters, including activator type, temperature, persulfate concentration, persulfate doses, and metal type and concentration. Our analysis to characterize our experiments and identify our optimal conditions were a mixture of in-house and external analysis. In-house, we used total fluorine, total organic fluorine, and total inorganic fluorine measurements. And external analysis was a combination of PFAS analysis using EPA 1633 at an accredited commercial lab, as well as the TOP assay, or total oxidizable precursors assay, and the TOF assay, or total organic fluorine assay. When we're looking at different analytical methods to evaluate PFAS degradation, we have to identify the strengths and weaknesses of each method and build a comprehensive analytical portfolio to ensure complete characterization and mass balance closure of our investigations. Using LCMS-MS or EPA 1633 analysis, this allows for the quantification of a targeted list of PFAS using commercially available analytical standards. This allows for the determination of PFAS degradation and loss. The main drawback of using LCMS-MS analysis is that you cannot quantify PFAS that are not present on the method list. Therefore, if you have a high concentration of PFAS precursors or unknown PFAS compounds, using EPA 1633 analysis will not capture those compounds. However, we can employ the TOP assay, or the total oxidizable precursor assay. This oxidatively converts polyfluorinated compounds, often unknown PFAS, into our terminal PFCAs. This allows for the semi-quantification of our unknown PFAS compounds. However, the TOP assay itself is heavily impacted by complex matrices and can sometimes struggle to capture the whole comprehensive picture. For this, we can turn to our total fluoride or total organic fluoride measurements. This process destructively converts all fluorinated species into free fluoride, which is then quantified using ion chromatography or fluoride ion selective electrode. This allows for the quantification of all fluoride present in a sample. However, the main drawback with total fluoride methods is that non-PFAS compounds such as PTFE and high inorganic fluoride can often convolute the results, making the closure of your overall analytical mass balance very difficult. So with this in mind, we can jump into our first set of investigations, looking first and foremost at our metal activator type. Classic metal activated chemical oxidations typically use iron or manganese or other multivalent metals for the activation of peroxide or persulfate. We looked at a variety of metals from silver, iron, manganese, copper, niobium, nickel, titanium, vanadium, cobalt, aluminum, tin, zinc, and a metal-free control. On our y-axis in our figure here, we have our single-dose PFOA degradation. So looking at the amount of fluoride that was released following the degradation of PFOA using a single dose of oxidant. And the conditions of our experiment can be seen in the top right of our graphic right here. We identified that silver is a novel metal activator for ISCO and demonstrates the highest amount of PFOA degradation at low temperatures. This trial was performed at 40 degrees Celsius. And once again, we'll be discussing a lot about degradation throughout this presentation. And for our purposes, degradation is the ratio of free fluoride generated from the destruction of PFAS measured against the total organic fluoride present at the initial start of that investigation. The biggest takeaway here is that not all metal activators exhibit the same performance at moderate temperatures, and silver is our best activator identified thus far. With this, we can now turn our attention to the role of temperature in degrading a variety of PFAS using silver-activated chemical oxidation. We identified that elevated temperatures, such as 60 degrees Celsius or 80 degrees Celsius, result in the highest degradation of 6,2-FTS, PFBA, and TFA. However, inversely so, we identified that lower temperatures, such as 40 degrees Celsius, resulted in the best degradation of PFOA. Once again, on our y-axis, we have PFAS degradation, measured as a percentage of the total organic fluorine present, and our x-axis is our various PFAS that we've investigated, and this is a single-dose oxidant study. So we've used one injection of oxidant to identify how much PFAS can be degraded. One of the most interesting takeaways as well is the fact that by using silver, we can actually initiate the degradation of 6,2-FTS under room temperature conditions. This overall process identifies that while elevated temperatures is efficient for degrading PFAS, this is a high energy process. And by shifting to 40 degrees Celsius, not only can we maximize our degradation of PFOA, but we can still meaningfully degrade other PFAS that we are investigating. We can now turn our attention to our initial persulfate concentration. Initially, we theorized that PFAS degradation would increase with increasing persulfate concentration. Our overall theory was that if you add in 10 millimolar of oxidant and you see a certain amount of PFOA degradation, if you add in 10 times that concentration of oxidant, you would hopefully see 10 times that amount of degradation. However, what we identified was actually the opposite of that. We identified that too much persulfate actually inhibits PFAS degradation. The reason for this is that high concentrations of persulfate, the generated oxidizing radicals actually interfere with each other and the persulfate molecules themselves, actually inhibiting and self-cannibalizing your reagents that you're adding. Furthermore, we identified that you actually end up with a diminishing returns effect as you add increasing concentrations of your oxidants. By taking the ratio of our PFAS degradation to our persulfate oxidant, we can see that persulfate is most efficiently used at lower concentrations. For example, by taking the amount of PFOA degradation at 10 millimolar of persulfate and dividing it by 10 millimolar, we see a persulfate efficiency number, which is our fluoride in milligrams per liter, divided by our millimolar of oxidant of approximately 0.022. And as we increase our persulfate concentrations, the amount of our persulfate efficiency actually drops down quite dramatically. This tells us that one single dose of high concentration of oxidant actually will not degrade a significant amount of PFAS. Therefore, multiple doses of low concentration oxidant is ideal to optimize your overall PFAS degradation. We then wanted to carry on further with that information and identify the effects of multiple persulfate doses. In our graphic here on the right, we have once again a variety of PFAS, including PFOS, PFOA, 6,2-FTS, PFBA, TFA, 6,2-FTS plus 1,000 milligrams per liter of humic acid, and an inorganic fluoride control that was carried throughout our experiments. We have PFAS degradation on our y-axis, which once again is the ratio of our inorganic fluoride generated to the total concentration of fluoride present. And in our legend here, we have the number of doses that we cumulatively added to our experiment. We would add a dose, wait 24 hours, take a measurement, and then add another dose. And we continued this for 8 total doses. Our initial investigations of data that we presented before this identified single-dose PFOA degradations of 4 to 6%. However, early optimizations of temperature, persulfate concentration, and silver concentration increased our overall initial PFAS degradation rates substantially. We identified that after 8 oxidant doses, PFAS degradation ranged from 34% to 88%, excluding PFOS. While initially resistant to degradation, we did identify PFOS degradation at higher doses of oxidant. This suggests that more extreme conditions, such as higher oxidant concentrations, are necessary to facilitate initial degradation of PFOS. And the higher recalcitrance of PFOS compared to other PFAS is well understood and well published in the academic literature. So this observation here was not necessarily unexpected to us. This graphic here identifies the cumulative persulfate concentration on our x-axis and related to our number of doses on our upper x-axis right here. As we can see, as we increase our cumulative persulfate concentration, or as we add more doses of persulfate into our system, we see a steady linear increase in our PFAS degradation. This relationship between PFAS degradation and cumulative persulfate concentration actually followed a strong linear relationship across 8 doses for PFOA, 6,2-FTS, PFBA, and TFA. This allows us to develop a model to predict the concentration of persulfate required to achieve greater than 90% degradation. We identified for a compound such as TFA, or trifluoroacetic acid, which is a very small compound, we would only need about 0.435 molar or 400 millimolar of oxidant to completely degrade TFA. For PFOA, which again is a much larger compound with more carbon-fluorine bonds, we would need a lot more oxidant to achieve overall degradation. These results are very exciting, and the fact that they follow a linear relationship will allow us to model and predict the overall requirements when treating PFAS on a site. This also does identify to us that further optimization is required to improve our overall treatment results and reduce the amount of oxidant required to achieve complete PFAS degradation. One of the biggest takeaways of this study was looking at the robustness of hot ISCO in the presence of common matrix interference, such as humic acid. As you can see in the graphic here on the right, we have humic acid at an initial concentration of 1,000 milligrams per liter. The solution itself is very dark and opaque. It is impossible to see through. However, while 1,000 milligrams per liter of humic acid slightly inhibited the first dose effectiveness of ISCO, subsequent doses were not impacted. Not only do we see 6,2-FTS continue to be degraded in the presence of 1,000 milligrams per liter of humic acid, but we see rapid decoloration and destruction of that humic acid in our samples. Going from dose 1 to dose 4 and 5, we see nearly complete removal of humic acid, as indicated by the loss of color in our system. This identifies that not only is hot ISCO capable of degrading PFAS in situ and ex situ, but it identifies that it can degrade PFAS in complex matrices and under extreme environments and conditions. Overall, we've identified a lot of different really interesting data and studies in our initial lab development phase, but there's three major takeaways I want to highlight before turning it over to Christy. We identified that silver is an ideal metal catalyst because it results in the best activation and highest degradation of PFAS. And as a catalyst, it can be used at very low concentrations to initiate the process. For persulfate, we identified that low concentrations and multiple doses of low concentrations are most appropriate to maximize PFAS degradation. And we identified that moderate temperatures, such as 40 degrees Celsius and under, allow for the effective degradation of PFAS. With this in mind, I will now turn the presentation over to Christy, who will discuss our results from a field demonstration.
All right, thank you, David. So yep, as David indicated, now I'm going to talk about a field demonstration of the hot ISCO technology, which we executed last year at a real-world site. In this trial, we treated 800 gallons of extracted groundwater, which was heavily impacted by PFAS. I'm going to try to grab a pointer to help me show you the data. Okay, oh, sorry, went too far. There we go. So this slide presents the baseline results of the groundwater that we treated. The initial characterization of the groundwater was by method EPA 1633. That's shown here on the graphic in the middle. Oh, I already lost the pointer. Maybe I will proceed without it. Let's try one more time. All right, so we have EPA 1633. And as you can see, this is identified a PFSA dominant PFAS profile. So the PFSAs are shown in this orange color grouping, and then PFCAs were indicated by these blue colors. And so total PFAS detected were over 250 nanograms per liter. So that's a pretty high concentration. And then PFOS was making up 200 nanograms per liter of that composition, shown here in the dark orange. The second highest then was PFHXS, which was here at about 45,000 nanograms per liter. And as David discussed, our hot ISCO lab trials had indicated that degradation of PFSAs is the hardest and slowest and most complicated to get going. So this was a pretty challenging real-world matrix on which to apply this technology. We also theorized that this mixture could contain up to an additional 100% of PFAS present as other precursors, as ECF precursors, which wouldn't be identified in this EPA 1633 targeted results. So we performed a total oxidizable precursor, or TOP assay, to investigate those precursors. So a reminder that TOP assay works by oxidizing precursors that are undetectable in the 1633 to more readily detectable PFAS compounds, allowing for a more comprehensive assessment of the total amount of PFAS in a sample. So the post-TOP assay analysis confirmed our suspected additional PFAS load. So you'll see there was like a 78% increase in PFCAs, so shown here in the blue, as a result of the TOP assay procedure. So this told us that we would fully expect to see an initial increase in PFAS concentrations as we did our treatment, as those precursors were oxidized. Then we also performed fluorine assays on the baseline samples with the fluorine equivalency pre-TOP and post-TOP, mimicking the TOP assay results up above. And then we also did extractable organic fluorine and absorbable organic fluorine analyses. So both of these are analytical methods used to assess the overall presence of PFAS in an environmental sample. AOF measures fluorine that can be absorbed onto a sorbent, while EOF measures fluorine that can be extracted from the sample using an organic solvent. So these methods provide a quick and cost-effective way to screen for PFAS. They're not providing information about like specific identity of the PFAS compounds present, but they provide that quick indication of overall PFAS levels. And those baseline EOF and AOF results also support the presence of the additional non-targeted PFAS. All right, so this slide is showing our field demonstration setup. We split the extracted groundwater into 3 separate 275-gallon totes. Each tote was set up as shown in the schematic. So some key pieces to note are the submersible heater. The work was done in September at a latitude of like 43 degrees north, which meant it did cool off each evening. So we did have to provide some heating to get the water up to that 48 degrees Celsius target and then to maintain it there. We also wrapped the totes in insulating blankets, which you can see in this picture here on the right. And then also note the circulating pump here in the bottom of the tote, which we use to circulate the water in the tote and help distribute the amendments. So then our metal catalyst was added once into the tote at the beginning of the field demonstration, and then persulfate oxidant was added in 9 separate doses, kind of mimicking that procedure that David was describing in the field. So this slide is now showing the PFAS results by EPA method 1633 analysis throughout the course of the treatment. So results are shown in nanograms per liter on the y-axis, and then the dates of our sampling events are shown on the x-axis. The times when oxidant was added are shown by the gold star. So you'll see those here at the top of each sample result. The first 3 samples here were from September 3 to September 5th. We then took a slight break between September 5th and September 13th for kind of some staffing operational reasons. And then we resumed September 17th and completed oxidant applications twice per day until the morning of September 20th. So those twice per day oxidant applications are identified by the AM and PM labels. So each of those days we had an oxidant dose added and collected a sample both in the morning and the evening. And then we took some post-treatment samples on September 25th and then again on November 19th. So what you'll notice in the first 2 samples is that increase in PFAS concentrations. So that initial dose of oxidant converted the unknown PFCAs. So you'll see there's like really not that many blue compounds shown here on the map. And then suddenly there is this increase in blue PFCAs. So as we knew from that baseline top assay and the fluorine results, this wasn't surprising. We were expecting to see that increase in the PFCAs from the transformation of the precursors. So then dose 2 likely continued to convert some of those unknown PFAS to PFCAs while also degrading PFAS. So you'll see that first big drop kind of back to initial concentrations, but that the PFAS profile had changed, right? There's like a lot more blue PFAS compounds showing. So then there was no change while we paused from September 5th to September 17th. And that's likely due to the oxidant that had been added before being exhausted. But another interesting thing we pulled out of that data is that since the concentrations remained stable over that time, it actually indicated that we didn't have any significant absorption of the PFAS to the walls of the totes during that downtime. So that's a nice confirmation that the storage materials used in the test didn't impact the PFAS results. So then subsequent oxidant additions later in September on the twice per day applications facilitated the additional PFAS degradation. By September 25th, or 3 weeks after starting the field demo, there had been a 95% reduction in quantifiable PFAS. And then that held steady in the sample that we took 2 months later. So this study demonstrates a decrease in the PFAS concentrations, including PFSAs and including PFOS, which are more challenging to oxidatively degrade, as demonstrated by the lab results that David presented. So these results are suggesting that the oxidant applied and the reaction conditions generated during the field study in this complex matrix were suitable to degrade PFSAs. So one of the goals of our study was to assess fluorine mass balance to evaluate the effectiveness of PFAS mineralization, or that complete destruction of PFAS. The degradation of targeted PFAS is documented by the results of EPA 1633. So that's kind of represented here by this dark blue circle. However, we had planned to include non-targeted analytical methods to better understand the degradation pathways and close the fluorine mass balance as much as possible. So although 1633 provides you that information about that targeted list, total fluorine analysis encompasses total PFAS in a sample, including an understanding of the non-targeted PFAS, which can't be seen by a 1633 analysis. So unfortunately, our end of study fluorine analyses were hindered by matrix interference. We were unable to resolve total fluorine both at an external lab and at our in-house lab. And then another thing I wanted to point out was that we had observed slightly increased reporting limits in EPA 1633 method by the end of the study, also likely due to that matrix interference. So this prevented us from observing low concentrations of targeted PFAS. Some of our reporting limits were like in the 500 nanograms per liter range up to, like 2,000 nanograms per liter. Then in addition, we did encounter some other aqueous chemistry during this field trial, including low pH, potential impacts from the salt content of the water, the required elevated silver concentrations because of the metal activator used, and then analytical challenges due to the matrix interference from that complex matrix. So each of these are items that we're going to be continuing to explore and which will need to be considered and evaluated ahead of future work. So we threw a lot of data at you today. So like, what does it all mean? And like, where does this technology work best? So HOT-ISCO has been evaluated against a diverse range of PFAS profiles as shown by the lab work David presented, as shown by that PFSA dominated matrix that we had in the field demonstration. The lab studies indicated that PFOS was the hardest to degrade, but the field demonstration showed that we did degrade PFOS and other PFSAs. Our lab studies have indicated that, HOT-ISCO is capable of degrading all of these listed PFAS profiles. Then also our applications have been performed on complex matrix types, including a variety of real-world groundwater, high humic acid samples, and high ionic strength systems, indicating that HOT-ISCO is capable of degrading PFAS in all of these complex matrices. We demonstrated greater than 95% degradation of PFAS in field trials, including the one shown here today. And that was been determined by the EPA method 1633 analyses. As I said, we'll plan to continue to do fluoride analyses to try to close that fluorine mass balance. So what are some scenarios for a HOT-ISCO application? First, of course, PFAS impacted media, whether that's from an AFFF release site. So AFFF is aqueous film forming foam, one of the most common releases of PFAS chemicals to the environment at airports and other locations for firefighting purposes. Other industrial PFAS uses, industrial wastewater that contains PFAS, source areas or high concentration waste. So one thing to note is that this technology is going to be most cost effective for treating high concentration areas. It's not going to be well suited for treatment of a dilute groundwater plume, but at a fire training area or a high concentration area near the PFAS release, yes, like that field demonstration demonstrated that we have the capability to degrade, concentrations up to hundreds of thousands nanograms per liter. So can be applied at really high concentration areas. So to wrap up with some conclusions, HOT-ISCO is a patented metal activated elevated temperature, up to that 40 degrees Celsius range, chemical oxidation technology for PFAS remediation. Metals and that small temperature rise combine to provide a low energy activation of the oxidant. So as I started with at the very beginning of this, sustainability is something we think about, and this is one that really does use lower energy requirements as compared to those other like the UV and high thermal activations of chemical oxidation. This technology has the potential for ex situ and in situ application. So that's innovative, especially for the in situ PFAS degradation perspective, because as of now, the only other technologies on the market that are really kind of like in situ sorption and stabilization methods, which aren't degrading the PFAS, or methods that concentrate PFAS from the subsurface and then like extract them and treat them above ground, or something like TRS Group's thermal conduction heating, which can be used for the removal of PFAS in vadose zone soil. But the in situ application of HOT-ISCO could be applied to saturated soil and groundwater. So therefore, it has potential to fill a large gap in the current PFAS remediation market. So what's next for our work? Some items that we plan to keep exploring as a part of our future investigations are the conditions and mechanisms for degradation of PFSAs specifically. We want to keep looking into what are the requirements to get that more complex, harder to degrade PFAS compound to degradation, which we saw in that field demonstration. Reagent dosing optimization. Our team's going to keep expanding on the types types of lab studies that David presented today. The optimal reagent dosing will likely vary by PFAS mixture. So we're going to continue to explore ideal dosing for a full range of real world scenarios. Then fluorine mass balance, degradation, and defluorination efficiency. So we want to understand, each of these is a key to any PFAS remedial technology. So we're going to continue to add fluorine analyses to our studies and hope to resolve some of those analytical challenges that we encountered in this field demonstration with the goal of documenting fluorine mass balance. Finally, we plan to look at the applicability of hot ISCO to other types of PFAS issues, whether that's biosolids, landfill leachate, potentially regenerating spent sorptive media like granular activated carbon. So a whole slew of options we could still look into. So we're going to continue to look for ways to bring this technology to market to fill gaps in PFAS treatment needs. And we hope that hot ISCO will be used as just, one technique in the PFAS remediation toolbox. And then finally, we want to thank all our other contributors who have been supporting this project through research and development, management, experimental design, analytical tasks, and then our field demonstration. So special shout outs to Dan Griffith, Lauren Turner, Ryan Thomas, Abby Bazin, Natalia O'Connor, and then the field staff who helped with this most recent field demo, primarily Drew, Charles, Gabe, Eric. This work couldn't have been done without all of you. And with that, we will be happy to take your questions.
Thank you, David and Christy. It was a great presentation on some of the latest advances on in situ remediation of PFAS. These are some really exciting results to see, and I'm sure there'll be more to come in the future. If there are any questions, you can raise your hand to ask it live now, or you can enter your question into the chat feature. And if there's any questions that we don't get to by the end of the webinar today, you can feel free to reach out to Christy or David directly. Their contact information is here on this slide. So we got quite a few questions already coming into the chat. So the first question is from Hao Zhang. There's a growing pattern of using pre-concentration technologies to further drive efficiencies in remediation technologies. Do you see that as an option for hot ISCO?
Christy, I can take that one.
Okay.
Excellent. So I think based on publications in the literature as well as presentations we see at various webinars or CERT BSTCP conferences, we see both IXR as well as foam fractionation being the two most common pre-concentration techniques. So for those who aren't aware, a pre-concentration technique is effectively an attempt to remove PFAS from a large volume of low PFAS concentration material and make it a small volume, high PFAS concentration solution. This is either done using foam fractionation, so effectively bubbling air or gas through a given liquid to effectively partition the PFAS into the bubble phase, which is then collected, condensed, and treated, or using IXR to remove it from the, again, low PFAS concentration aqueous matrix, and then store it and concentrate it on that IXR, and then effectively regenerate it using either thermal or chemical activation processes. The main difficulty with pre-concentration techniques is it ends up being a very highly complex matrix to treat, both high in PFAS concentration and typically high in the presence of dissolved organic matter. As we demonstrate in our presentation, hot ISCO loves high PFAS concentrations and does not care about complex matrices such as those present in high ionic strength solutions or dissolved organic matter. So do we see pre-concentration techniques being used for hot ISCO? Absolutely. I think it's safe to say that is an area of interest for further study with our experiments, and it will only further increase the applicability and use case for hot ISCO.
Yeah, and I'll just tack on to that I think a treatment train approach for PFAS remediation in general is going to be very important. Like there's no one technology that's going to solve everything or be capable of handling any situation. So for PFAS remediation at a real world site, we'll have to be looking at the application of multiple technologies together. So I think that's a great demonstration of the one way to combine multiple technologies to get to a more effective solution.
All right, thank you guys. Next question is from Emma Sauer. In your analysis section, you mentioned that you do both in-house total organic fluoride analysis as well as external accredited analysis. Why do you do both?
Great question. So the ability to leverage in-house analysis, which is something that we've developed recently here at Parsons, allows us to investigate a broad number of experimental conditions and variables, one, very quickly, very inexpensively, and allowing us to generate results pretty much same day, if not next day. This allows us to really investigate a lot of these variables quickly and thoroughly. And then these results are confirmed using external lab analysis to effectively validate our in-house analytical techniques, and allowing us to proceed with results while we're waiting on the data from commercial labs to come back to us. Average commercial turnaround times these days is anywhere from 10 days to 25 days. And needing to wait for that commercial analysis data to come back before proceeding makes R&D very difficult and slow. So leveraging that in-house analysis allows us to really just fire away at very, very rapid pace for R&D here at Parsons.
Okay, next question is from Tom Lee. Any theories on why PFAS was better degraded in the field than in the lab, perhaps temperature?
Christy, I can jump on that one.
I know, I was going to say, you want to take that one first, and then I'll tack on.
So there's a lot of publications in the literature that actually identify enhanced degradation of a variety of technologies when you shift from a laboratory environment to a field environment. And that can often be because of the unique combinations of geochemistry and radicals that can be generated when you have a realistic world sample. We're studying single metal activators, just silver, just titanium, just vanadium. But as we're all aware, in groundwater, there can be very, very low concentrations of a diverse range of metals. So it is possible that there is some emergent property present in the geochemistry of the groundwater that is facilitating enhanced PFAS destruction. Furthermore, and I'm just going to go to the data presented by Christy, it's important to note that the conditions presented here for our field study represent a very, very high oxidant load scenario. I believe each dose applied here was 200 millimolar. And the reason for the higher dose concentration is because this is groundwater. It's a more complex field site. So we increase the number of doses as well as the concentration of each dose. So effectively, we see significant PFAS removal at doses effectively 4 through 8, which is the equivalent of 800 millimolar to 1.6 molar of persulfate. These conditions result in a low pH, high ionic strength environment, which is just the extreme environment you'd expect to identify PFAS degradation in. As Christy and I discussed, future efforts are looking into effectively closing the mass balance and better elucidating PFSA-specific degradation mechanisms. But that is our main theory as to why we're seeing enhanced PFAS loss and degradation in our field studies. More oxidant, more unique combination of metal activators, and a more diverse range of PFAS with which to kind of destroy.
Yeah, that's a wonderful summary. I will just add on, and of course, we could get really technical here and stay really technical. So sorry if this is too high level, but for those of you that might be interested, we've been bouncing around the idea of desulfonation occurring. So that's where, basically, the conditions would allow for the process of removing the sulfonic acid group from the PFSAs and converting those into PFCAs. So if that was occurring, then basically the PFCAs that are generated by that process would then be more susceptible to the degradation that we observed in the lab. So that's the process that we're considering. What was spurring that, whether it's like the conditions that David was describing in the real world setting. As he said, we're going to keep exploring why that's happening.
Okay, the next question is from Faith McDonald. You identified silver as the best metal activator, but as silver is considered hazardous, what precautions would you have to take to use it for PFAS degradation?
Yep, so great point. All the work we've done has identified silver as the metal that is, optimal for degradation here. But that is regulated as a Resource Conservation and Recovery Act, or RCRA, hazardous metal. So silver at low concentrations is acceptable, but when silver is present above the regulatory threshold of 5 milligrams per liter in water or in leachate from soil, that's considered hazardous. It has to be managed as hazardous. So for our field demonstration that we presented today, we did use silver as the activator, but since it was ex situ, the materials were contained during the treatment study. And then at the end of the study, we actually recovered the silver by filtering the water through an ion exchange resin. So we now are going to try to recover the silver from that ion exchange resin and attempt to reuse it in future hot ISCO studies. So for ex situ applications, less of a big deal. But for an in situ application, it becomes more important because any metal activator is going to remain in the subsurface, and we wouldn't be able to recover it in that same way that we did for the ex situ demonstration. So we'll have to dose the silver in a concentration that is going to be regulator approved and present in or distributed in the treatment area at a concentration that's acceptable. So that means that's why we're doing this work, to try to optimize the silver dosing and also continue to look for other metal activators or combination of activators that might give us a different innocuous option for the activation. So our lab team continues to explore that.
Next question is from Adam Westcount. What do you see as one of the biggest challenges when applying hot ISCO to a new field site?
See, I can jump on that one.
Go for it.
One of the biggest challenges with ISCO is identifying the initial oxidant concentration and the concentration of subsequent oxidant doses when applying it to the site. Even though we saw that ISCO is able to handle robust, organic, rich, and metal and ionic strength rich environments, the presence of those materials will still consume some of that oxidant that we require for PFAS degradation. So effectively, what we would like to do when applying this to a new site is really identify this relationship that we presented right here. Effectively applying a small number of doses in different concentrations to identify the relationship between PFAS degradation and cumulative persulfate concentrations. This would then allow us to identify the model and identify how much oxidant would be required to degrade PFAS rapidly on site. So to answer your question, if benchtop trials are an option to effectively optimize our conditions in the lab before applying it to the field, that would resolve a lot of the challenges associated with applying it to a new field site. Besides that, the biggest challenges would effectively be identifying the overall geochemistry and any kind of complex matrix components such as co-contaminants present on the site.
We'll take another question or two and then we'll wrap up, but we've got a couple more. Regarding hazardous wastewater treatment, for example, petrochemical, is it fair to say that hot ISCO can be applied as a tertiary treatment?
Yes, I would say absolutely. This can be combined with other treatment methodologies. And I mean, David, feel free to step in and correct me, but petrochemical industry treatment, I feel like, would jive well with the information we have for hot ISCO's capability to work on complex matrices. And do you agree with that?
Absolutely. There's a lot of literature available both within our own R&D program as well as published that identifies chemical oxidation itself as a fantastic tertiary treatment to petrochemical wastewater. Short answer, yes. ISCO should have no problem treating wastewater generated from petrochemical processes, either primary, secondary, or tertiary. Humic acid is a very complex organic matter, and it chews through that without issue. The chemicals present within petrochemical waste should be just as easy to oxidize through with ISCO.
And since we're almost at the end of the webinar, I'll take one last question. What makes it hard to keep hot ISCO energy efficient and affordable when used on a larger scale to destroy PFAS?
That's a great question. And we haven't quite gotten to large scale, so we'll be working on this. But I think From my perspective, the things that I see is going to be hardest is the water heating. I feel like from affordability standpoint, the reagents are affordable. So that part's going to be simple. I think the energy efficiency of heating the water at a larger scale would be the one thing. But as we said, this is much lower energy as compared to all the other activators out there. So I think overall, it's still going to remain a comparatively energy efficient technology.
I don't know if I would apply ISCO in like Antarctica. I think you'd have to get a lot of insulation to make sure that you keep it heated. But yeah, Christy, that's the perfect answer. You nailed it.
Okay, well, I think that's a wrap for us today. If we can go to the final slide about our next webinar. So our next webinar will be on July 9th on bioaugmentation for the microbial degradation of 1,4-dioxane, presented by Lauren Turner at the same time, 12:30 to 1:30 p.m. Eastern. If you have any other questions that you didn't get a chance to ask today, please feel free to reach out to David or Christy directly. And as mentioned, a link to the form for pH credit has been posted in the chat several times throughout the webinar. And if you have any issues downloading that form or accessing it, please let us know and we can help out with that. And if you missed any of the questions or content today, a recording of this webinar will be posted on our YouTube channel in the next few days. Thank you to everyone who joined us for today's webinar. We hope to see you again in July.